Good morning. Today we will discuss about the counters. We will start the counter section from this class, and we had already come across the JK flip-flop, hope you remember, and we know the property of the JK flip-flop. One property is that the race condition, it is the major drawback of JK flip-flop. We know that we are not using this condition here. Instead, we come across the race condition by two methods. We had already discussed the two methods. Either we can connect JK flip-flop in the master-slave mode, or we can use negative edge triggering. See, here we know the clock is applied here. This indicates this is the edge and this is negative edge triggering. And the major difference in this connection is that first clock is applied only to the, this clock is applied only to the first flip-flop, and the clock to the second flip-flop is given from the output of the first flip-flop. That is the most important thing to be noted in counters. That is, the output of the first JK flip-flop is provided as input to the second JK flip-flop. That is the most important concept here. And we use toggling here. We had already discussed what toggling is. The major drawback of JK flip-flop was that when we provide the input j equal to 1 and k equal to 1, race condition arrived, and now we overcome the situation by connecting it, by giving the clock pulse in negative edge triggering mode. And also we had connected, this connection is known as master slave connection. We are using the edge triggering mode, and so we are setting this in a toggling mode. Is that clear now? And see, we have 4 clock pulses. This is the initial clock, and let the frequency of this clock be Fc, and we have the frequency Fa here. Okay, this is the frequency of this clock, the first clock, and this is the frequency of the second clock. This is our flip-flop 0, and see, the output here is QA. This clock becomes active in the falling edge. The clock becomes active in the falling edge. That is, if the previous state is Q, the output will be Q complement. That is, if the previous state was 0, the present output will be 1. If the previous state was 1, the present output will be 0. And let us see the QA, the output of the first flip-flop. This becomes active only during the falling edge of the first clock. Okay, this becomes active only from the falling edge of the first flip-flop, and due to the property of the JK flip-flop, we know in the next stage the previous stage will be complemented. Here it is 1 and here it is 0. Again here in the next falling edge, it will complete the pattern like this. That is, this is how the output of first flip-flop look like. Okay, and this clock is only for the first flip-flop. We provide this clock as input for the first flip-flop only, and the second flip-flop, the clock to the second flip-flop is QA. That is, the working of this flip-flop is based on this input. And see, we know this is negative edge triggered flip-flop, and this flip-flop works only when the first level falls from the high to low in this clock. See, here it is active low, and the QB, it becomes active in this position. This is how it looks like. that is the QB output. This output is available only when this edge trigger at this point, that is in this edge triggering, when this clock falls from high to low, at this point QB becomes active. Okay. I'll repeat, this clock is, the clock pulse is for the first flip flop. This flip flop works when the clock falls from the high to low, and here we had plotted how QA works, and the QA is given as input. Depending upon the QA signal, at the falling edge of the QA, only at the falling edge of the QA, QB will be active. Is it clear now? And now we will see, this is the time period. This is the time period for the first clock. Okay. The time period for this clock is Tc. Let the time period for this clock be Ta, and the time period for this be, we know the relation F equal to 1 by T, where T is the time period, and we will see the time period Ta is equal to 2 Tc. We will calculate the frequency for the QA, and which implies 1 by Fa is equal to 2 Tc, means 2 by Fc. Okay. And therefore Fa is equal to Fc by 2. This is the frequency division in QA. And next we will see the Tb, which is equal to, Tb is equal to 2 Ta, 2 times Ta, that is 2 Ta, and which means 1 by Fb is equal to 2 Ta, means we have Ta is equal to Fc by 2 Fc, okay, which is equal to 4 by Fc. Therefore Fb is equal to Fc by 4. So this is the frequency division in QB. Okay, this is the frequency division in QB, that is Tb, we get Tb is equal to, Fb is equal to Fc by 4, where Fc is the clock pulse for the first flip flop. So this is the relation between the time period and the frequency. We got the frequency division for each clock pulse in the flip flop, that is for Ta it is Fc by 2, and for Tb it is Fc by 4. If we have p number of flip flops, then we can have 2 raised to p number of divisions, frequency divisions. Here we have 2 flip flops. We had considered 2 flip flops, then we have 2 raised to 2 equal to 4 number of frequency divisions. And we know the counter circuit is used to count from any starting point to any ending point. For example, you can perform the counting operation from 0 to 10 or from 8 to 16, it is up to the application. Okay. And we will see a truth table for this. Here we have the clock as input, QB and QA. Initially, when the clock is 0, we know the clock is 0, at that time QB is 0, QA is also 0. This is the combination. When the clock is 1, okay, when the clock is 1 in this clock pulse, okay, in the first clock pulse we will see the value of QA and the value of QB. Here QB is 0 and QA is 1, and we will plot it like this: QB is 0 and QA is 1. And in the third clock pulse we will see we have QA is 1 and QB is 0. See, in the second clock pulse, that is not 1, this is 2. In the second clock pulse we had seen that QB was 1 and QA was 0. And in the third clock pulse, we can see that QA is 1 and QB is 1. Okay. Now, when we consider the decimal equivalent of these combinations, we get 0, 1, 2, 3. That is, during each clock pulse, we are performing a counting operation from 0, 1, 2, 3, etc. And we had seen that if there are p number of flip-flops, you can perform 2 raised to p number of divisions. Here we can perform only the counting operation 4 operations, that is from 0 to 3. If you want to perform the counting operation from 0 to 16, what should be the value for p? P should be equal to 4. Okay, that is 2 raised to 4 is equal to 16. There should be 4 flip-flops. This is how the circuit works. And if we continue executing, giving more clock pulses, if we again give the clock pulses, or if we continue executing the circuit, it again completes one cycle and begins from 0. Again it starts from 0, 0, 0, 1, 1, 0, 1, 1, because we have only considering 2 flip-flops here. Okay, we had already seen that if the number of flip-flops is 2, the maximum number of frequency divisions will be 2 raised to p. Here we have only 2 flip-flops. We are considering only 2 flip-flops. So, the maximum frequency divisions, that is, we will see by counting the frequency divisions, we can get that is how we perform the counting here in the counters, which is equal to 2 raised to 2. We can count up to 4. If you want to perform the counting operation up to 16, how many flip-flops would you require? 4 flip-flops. That is, to count from 0 to 15, you require 4 flip-flops. That is 2 raised to 4 is equal to 16. So, you will get 16 frequency divisions. That is all about the counters. Hope this is clear for today. And that is all for today's class. Thank you.